today we are going to see some more interesting and important questions from Narendra Avasthi's physical chemistry, mole concept. Come on, let us discuss few more questions from this session. Here, the first question, 44 gram of sample on complete combustion gives 88 gram of carbon dioxide and 36 gram of water. The molecular formula of a compound may be. See, here we have to find out the molecular formula. And first and foremost, we have to identify the number of moles of carbon and hydrogen and oxygen so that it will be easy for us to identify the molecular formula. Okay, now the first one, what we have to identify, the formula of a hydrocarbon which is having 44 gram. Okay, now here I just mentioned here CXHYOZ plus X plus Y by 4 minus Z by 2 O2. It gives XCO2 plus Y by 2 H2O. So this is actually a simple formula to identify the answer, right? Okay, now what is that 44 gram they mentioned, so this hydrocarbon actually it is having 44 gram of a sample. This is the sample. So this is actually the sample. Now in that we are having what it is here, carbon dioxide, how much we are getting? 88 gram of carbon dioxide and 36 gram of water. So they have given that actually this is a given mass, like, so molecular mass we know very well, so we will get the number of moles. Next thing, how many moles, according to that we can identify the molecular formula. Come on, let us discuss here number of moles to identify. Okay, number of moles of carbon dioxide and water, right? So here moles of carbon dioxide, moles of carbon dioxide. So moles of carbon dioxide, given mass how much? It is 88 gram and molecular mass of carbon dioxide, it is 44 gram per mole. So you will get what it is, this gram and gram will be cancelled, so you will get what it is, 2 moles. So here actually number of moles of carbon dioxide, it is 2, right? So number of moles of carbon dioxide, I just mentioned here number of moles of carbon dioxide, it is 2 mole. Right, got it. Now the same way water molecules also. So number of moles of water, here they mentioned given mass what it is, 36 gram and molecular mass of water, it is 18 gram per mole. So you will get what it is, here also you will get 2. See here gram and gram will be cancelled, here also 2 moles. Right, now number of moles of water. So number of moles of water, how much? 2 mole. Right, now here both the thing we got it, number of moles of water and number of moles of carbon dioxide. Now we have to identify the number of moles of oxygen. For that, let us go and identify here actually carbon dioxide and water. Right, in that what it is, carbon, hydrogen and oxygen, we have to find out the number of moles. Here 2 moles of carbon dioxide and 2 moles of water molecules. For the 2 moles of carbon dioxide means here oxygen only we have to identify. For that, here 2 moles of carbon, right? So 2 into 12 plus here hydrogen 2 moles, no, so 2 into 2. So altogether how much we are getting here, actually what it is, 24 and here what it is, 4. So altogether what we are getting, 28, actually 28 of carbon and hydrogen. Now actually in the starting they have given the sample of the gram, right? Here they mentioned the sample of the gram, it is how much, 44 gram of a sample. So 44 gram of a sample, in that 28 gram we found carbon and hydrogen, it is 28 gram. So remaining will be what it is, oxygen only. So carbon plus hydrogen, so both together you are getting what it is, 28. So 28 and then here carbon plus hydrogen plus oxygen combined together, it is 44 gram. So that means this is 28 gram you consider. So 44 minus 28, you will get how much? That is gram. So you will get how much it is? Actually 16 gram. So 16 gram means oxygen 1 mole, right? Oxygen 1 mole. So here as we observed here, carbon how many? 2 moles of carbon, 2 moles of hydrogen. So 2 moles of carbon and 2 moles of hydrogen and oxygen 1 mole. So according to that we can identify the formula. So here 2 moles of carbon means C2 and hydrogen 2 moles means, now generally what it is, XCO2 plus Y by 2 H2O. So hydrogen 2 moles, already it is H2. Number of atoms, it is 2. So that moles, when we are considering carbon X means it is 2 moles. No, so carbon 2, hydrogen 2 into 2, that is 4 moles. And oxygen, actually atomic mass of oxygen, it is 16. So you will get what it is, 1O. So that means C2H4O. So that means what is the name of this compound? Ethylene oxide. Ethylene oxide. So what is the molecular formula of the C2H4O? So that is the compound, right? I hope you got the clarity. How do we identify the answer? Come on, let's go to the next question. Now the option it is C, C2H4O. So this is the way we found. Hope you got the clarity. Come on, let's go to the next question. 40 milligram of diatomic volatile substance X2 is converted to vapor that displayed 4.92 ml of air at 1 atmosphere and 300 Kelvin. Atomic mass of element X is nearly. Right now, they have given that diatomic volatile substance X2 and milligram they have given, and vapor that is displaced, what it is, 4.92 ml of air. So they have given the gaseous compound. So gaseous compound, what formula can we use? Okay, first and foremost, let us collect the data. So the mass of X2, it is actually here, mass of X2, it is diatomic molecule, it is actually 40 milligram. So 40 milligram we can convert it into gram. So that means 0.040 gram, right? Now the next one, volume of that compound. So volume, how much? Volume, it is actually 4.92 ml. So this also we can convert it into liter. So 4.92 into 10 to the power of -3 liter. Yes. Now the next one, pressure, temperature. How much it is pressure? Pressure, it is 1 atmospheric pressure, and temperature, it is 300 Kelvin. Okay. Now for that, one more thing, gaseous constant. So gaseous constant, how much it is, that is a constant, right? So this is 0.0821. That is actually liter atmospheric pressure per Kelvin mole, right? So this is the unit. Yes. Now number of moles we have to identify. So number of moles we have to identify means we have to use that, what it is, ideal gas equation. So number of moles using ideal gas equation. Ideal gas equation. So what is that ideal gas equation? PV equal to nRT. So here number of moles, it is N, no. So N equal to PV by RT. So values, that all the data we have provided here, no? Okay, come on, let us apply the value over here. So N equal to here, N equal to pressure, how much? 1 atmospheric pressure, and volume, how much? 4.92 into 10 to the power of -3 liter divided by R, it is gaseous constant 0.0821, right? 0.0821 into temperature 300 Kelvin. Right now, when you calculate this number of moles, you know how much you will be getting. So number of moles, that is diatomic molecules, no? So X2, that is actually how much we are receiving? 0.0002 moles. Right, we got it. Now, molar mass of X2. So molar mass of X2, what it is? We have to identify. So molar mass of X2. So it is a diatomic molecule, no? So molar mass of X2, it is given mass by what it is? Number of moles. So number of moles just now we found. Okay. So here molar mass, that is given mass, how much they have given here, what it is? 40 milligrams. Now we converted into grams. So that means 0.040 gram by number of moles, 0.0002 moles. So we are getting the answer here. How much we are getting the answer when we calculate it? So X2, molar mass X2 equal to how much? 200 gram per mole. So here gram per mole. Okay. So molar mass X2, they are asking the question, molar mass X2, right? Molar mass X2, that is gaseous compound, right? So that is 200 gram per mole. So generally, what is the unit of molar mass? It is gram per mole. I hope you got the clarity. Question they are asking, atomic mass. So this is actually molar mass, diatomic molecule, no? So that means element X, atomic mass only, no? So element X, it is actually element atomic mass, right? So X, atomic mass, element X or atomic mass X equal to what it is? So 200 divided by 2. So 200 divided by 2. Diatomic molecule, no, so divided by 2. So you will get what it is, atomic mass 100. 100 also gram per mole only, right? So X equal to what it is, 100 gram per mole. I hope you got the clarity now. Which is the correct option? Let us check how do we identify this complete idea. Yes, which is the correct option? Option D is the correct option. I hope you got the clarity. Come on, let's go to the next question. The next question, elements X and Y. X atomic mass is 75 and Y atomic mass is 16. Combined to give a compound having 75.8% of X, and the formula of the compound is. Actually, this is very simple question. They have given that what it is, X percentage mass, and Y we have to identify. Now let us assume the mass of the compound, it is 100 grams, so that easily we can identify the formula of the compound, right? So mass of the compound, how much it is, 100 gram. So in that mass of X, okay, mass of X, this is actually 75.8 gram we can consider. In that mass of Y, okay, mass of Y. So mass of Y, what it is, 100 minus 75.8. So you will get how much? So you will get around 24.2 gram. So 24.2 gram. So mass of Y, it is 24.2 gram. Now this is given mass of X, given mass of X and given mass of Y. So we will find the what it is, number of moles, because they have given atomic mass. So easily we can identify the number of moles of X and Y. Through that we can identify that ratio. Then finally we can consider that what it is, formula of the compound, right? Okay, now the first one here, number of moles of X. So number of moles of X. So number of moles of X equal to what it is, given mass by atomic mass. Right. So given mass by atomic mass equal to what it is, mass of X, what it is, 75.8 divided by atomic mass of X, what they have mentioned, 75, right? So 75. So it is gram per mole, no? It's gram per mole. Yeah, it's gram per mole, and here it is a gram. So when you calculate this, here you will get what it is. You will get 1.011 mole you will be getting, right? Then same way, number of moles of Y. Okay, so number of moles of Y. So the same way, given mass by atomic mass. Given mass, how much it is? We calculated, no? So 24.2 gram, and atomic mass is 16. So you will, this is gram per mole, right? So you'll be getting how much around here? 1.513 mole, right? So here smallest ratio we have to identify. Which is the smallest ratio? Here 1.513, here you are getting 1.011. So which is the smallest ratio? Means atomic mass ratio X and atomic mass ratio Y. Okay, so in that smallest ratio, it is what it is, X, it is actually 1.011 divided by smallest ratio, it is 1.011. Right, the same way here, Y, number of moles, it is 1.513 divided by 1.011. So both, when we consider, here you are getting 1 and here you are getting 1.5. So we have to find out the whole number ratio. So whole number ratio, this is 1 and this is 1.5. So multiply with 2. When you multiply with 2, you will be getting here 2, you will be getting here 3. So that means this is X and this is Y. So what is the formula you can bring over here? X 2, Y 3. So this is the formula you can provide. I hope you got the clarity. Come on, let us find the answer in this option. So X 2, Y 3. It is very simple, right? Right. So which is the correct option? Option D is the correct option. X2, Y3 is the correct option. Hope you got the clarity. Come on, let's go to the next question. Here, a sample of phosphorus that weighs 12.4 gram exerts a pressure at 8 atmospheric pressure and 0.821 liter closed vessel at 527 degrees Celsius. Molecular formula of the phosphorus. Actually, here also they are asking about formula, molecular formula only. Okay, come on. But here they have given what is it? Gaseous content way. Okay, so here vapor they mentioned. So through that we can identify. Okay, now here also the same. We have to find out the number of moles through ideal gas equation. Okay, let us write all the data so that it will be easy for us to apply the values. Right now here, sample, mass of the sample. Mass of the sample. Mass of the sample, how much it is? 12.4 gram. Right now here, pressure, how much? Pressure, it is 8 atmospheric pressure, and volume it is 0.821 liter, and temperature temperature it is 527 degrees Celsius. So we have to convert it into Kelvin. So here 527 plus 273 Kelvin. So altogether you will get 800 Kelvin, right? So temperature it is 800. And gaseous constant, okay, gaseous constant, gaseous constant. Gaseous constant, how much it is here? 0.0821 liter atmospheric pressure per what it is, mole Kelvin, mole Kelvin. Right now number of moles we have to identify. So number of moles we can identify through gaseous equation. Okay, so ideal gas equation, right? So number of moles through ideal gas equation. So ideal gas equation, PV equal to nRT. So PV equal to nRT. So N it is number of moles. So N equal to PV by RT, right? So let us apply all the values over here. So pressure 8 atmospheric pressure, volume it is 0.821 volume, and gaseous constant and temperature. Yes, so N equal to here pressure 8 into volume 0.821 divided by gaseous constant 0.0821 into temperature 800 degree Kelvin. Okay, now what is the value you are getting? You'll be getting around 0.1 mole. So N equal to 0.1 mole. Okay, now molar mass we have to identify. So molar mass, what it is? Molar mass equal to molar mass. Molar mass equal to what it is? Given mass by moles. So we can identify the molar mass. Given mass by moles. So we can identify molar mass. So given mass of the sample, how much it is? 12.4 gram divided by what it is? Number of moles. Number of moles it is 0.1. So we are getting how much it is? So we are getting how much? It is around 124 gram per mole. Right here mole, na? So here 124 gram per mole, that is molar mass of the sample. Right. Now here atomic mass of phosphorus, they are asking about what it is. Phosphorus vapor. No. So phosphorus vapor, what it is? Here phosphorus only they mentioned now. Atomic formula, molecular formula of phosphorus. So atomic mass of phosphorus, because molecular formula we found that is molar mass or molecular mass. Okay, now here atomic mass of phosphorus, it is actually 31 gram per mole, right? Okay, now number of atoms present in that formula. So number of atoms present in the formula. So how much it is actually? So here which point you can bring it? So here molecular mass by atomic mass. Okay, molecular mass, that is molar mass by atomic mass. So what formula you were using? Number of atoms present in that formula. So molar mass by atomic mass. So molar mass, just now we found what it is? 124, right? This is 124 gram per mole, right? Atomic mass, it is 31. So you will get what it is? You will get number of atoms, it is how much it is? 4. So that means phosphorus P4. So P4, 34 into 31 into 4, you will get 124 gram per mole. I hope you got the clarity, right? So given mass, it is, given mass how much? It is 12.4. Molar mass, it is 124. So number of moles, through that you can identify. Now, which is the correct option here? Option B, P4 is the correct option. So number of atoms, it is P4 in that molecular formula, it is P4. I hope you got the clarity. If you want, you can check with that number of moles also. Number of moles, it's what it is. Given mass by molecular mass. Given mass, this one. Molecular mass, that. And then number of moles you will get. So number of atoms present. So in that way, you can identify. So whichever the question, if they are asking also, if you know the concept thoroughly, you are able to solve. From that, you can check also whether the answer it is correct or not. Hope you got the clarity. Come on, let us go to the next question. The next question, manganese forms non-stoichiometric oxides having the general formula MnOx. The value of X for the compound that analyzed is 64% by mass manganese. Right now here, manganese, that is actually non-stoichiometric they mentioned. So non-stoichiometric, it is nothing. It is deviating from what it is, ideal stoichiometric. Now for example, FeO, so that means here 1 mole of iron, 1 mole of manganese, so 1:1. So that is a whole number ratio. But non-stoichiometric means it is deviating from simple whole number ratio. That means here FeO, here 1 mole and here 0.93 mole. So in that way, this is called a non-stoichiometric form. Right now, the same way here also manganese oxide, no, this also the same MnOx. So what is the value of X we have to identify? So general formula, what they mentioned, the general formula of manganese oxide, here general formula of manganese oxide. In that, manganese, how much it is? 64% by mass of manganese. In that, oxygen percentage we have to identify. I hope you got it. Now, total mass percentage. So, total mass percentage, it is actually what it is? 100. So, that means oxygen percentage, mass of oxygen percentage. How much it is? 100 minus 64. You will get what it is? 36%. So, mass of oxygen percentage is 36. Now, we have to identify what it is. The value of X. So, value of X, for that, what are the points to be noted down? Atomic mass of manganese, atomic mass of oxygen we have to identify. So, atomic mass of manganese. Atomic mass of manganese, what it is? 55 gram per mole. And the same way, atomic mass of oxygen. Atomic mass of oxygen, it is 16 gram per mole. Now, we have to identify that X. Now, for that, mass percentage of manganese, mass percentage of manganese equal to atomic mass of manganese divided by here total mass of MnOx. Okay, so here what we can write? Total mass of MnOx into 100. Okay, so this formula we can use. So let us apply the value here. Mass percentage of manganese, it is 64%. That is equal to atomic mass 55 gram per mole divided by total mass of manganese. It is 55 plus 16. This is X, right? So 16X. Okay, so this is actually 16 atomic mass of oxygen, X, that value, right, into 100, right? Okay, now, can we rearrange this point? Okay, 0.64 into 55 plus 16X, right, equal to 55, right, 55 equal to, here 55. Now, when we calculate this point, here we will get what it is. When we calculate these two, 0. This 35 you will get, right? So 35.2 plus 10.24x equal to 55. Okay, now we can bring this side 10.24, 10.24x equal to here 55 minus 35.2, right? So you will get how much? 10.24x equal to 19.8. You will be getting, right? So now x equal to 19.8 divided by 10.24. So you will be getting 1.933, right? So this is not a whole number ratio. That is what I just mentioned. Non-stoichiometric form means it is deviating from whole number ratio. That means it is a decimal form. So we have to convert it into whole number ratio. That is the reason. Right now here, atomic mass of oxygen, it is 55. Now, oxygen value, atomic mass of oxygen, it is 16. The value of X, the value of X equal to 1.933, right? So, MnX. So, here, MnOx. So, X value, it is 1.933. So, we can write here MnO2 because we can convert it. So MnO2, it is a correct format, right? Okay, now this is a non-stoichiometric form of that X value. I hope you got the clarity. What do you mean by non-stoichiometric form? How to analyze this question? Yes, come on, let's go to the next question. Now, which is the correct option in this question? So it is 1.93. See, 1.93, option D is the correct option. I hope you got the clarity. Come on, let's go to the next question. The next question, same like last question, what we have identified non-stoichiometric format, right? So here 1.44 gram of titanium, atomic mass it is 48, reacted with excess of oxygen and produce X gram of non-stoichiometric compound, titanium oxide, titanium 1.44 oxygen, right? So here value X we have to identify. Right now here in that, the same non-stoichiometric means that a simple whole number ratio is deviating from ideal stoichiometric form. Okay, now as we observe here, given mass they have given, right? Okay, 1.44 gram of titanium reacted with excess of oxygen. So number of moles directly we can identify. I hope you understand what do you mean by non-stoichiometric form, right? Okay, number of moles of titanium. So number of moles of titanium, it is given mass by molecular mass, right? So that means here 1.44 gram divided by molecular mass they have given, no, it is 48 gram per mole, Right, now here, what is that answer you will be getting? You will be getting 0.03 mole. Right, okay, now here what they have provided the data, that is titanium 1.44 oxygen. Titanium oxide they have given like that. So 1 mole of titanium contains 1 mole of titanium contains it is 1.44 mole. That means it has to be 1 mole only, but here they mention 1.44 extra. So mole of the compound. So moles of the compound. Moles of the compound. So what is it? Compound titanium oxide. Right, now here the moles of titanium divided by moles of titanium. Just now we found, no, that is given mass by molecular mass. So that is moles of titanium divided by what it is, 1.44 mole. So that is here given mass, no, that one. Right, now here you will get what it is. Here moles of titanium 0.03. Just now we got that answer, no, given number of moles. Here this is the answer we got it, no, divided by 1.44. 1.44. So you will be getting how much? Here you will get 0.020. 833 somehow. Okay, so this is small. Right, now here what is the answer? You are getting moles of titanium compound, you are getting this much. Right, now here molar mass of titanium oxide, atomic mass, constituents, all those things. Let us identify molar mass of titanium oxide. So molar mass of titanium oxide, it is actually here atomic mass plus constituent ratio. Atomic mass plus constituents, that is moles, na, constituents ratio. So here come on, let us identify. Titanium, it is 48 into 1.44 constituent, right? So here this one plus oxygen, how much? 1 into 16, right? These both combined, you will get how much? 85.12 gram per mole, molar mass. So according to this, here this point here, how much? It is 1.44 they have given, no? That is what titanium atomic mass into how much provided here, that is what. Right, now here molar mass we found. Now the total mass of X, here what is it? Total mass of X, here 0.0208. We can consider only 4 numbers. So here 3 is there, no, 0.083. Okay, 0.208 mole into 85.12 gram per mole. Right, now here how much you will be getting? 1.7733 gram. Right, now here the value of X, the value of X is 1.77 gram. Okay, come on, let us identify the option. I hope you got the clarity. How do we identify? Yes, and you got that idea. What do you mean by non-stoichiometric form? Right, now that is deviating from a whole number ratio, right? So the X, it is 1 point here. This is 1.77. Option B is the correct option. Hope you got the clarity. The next question, which statement is false for the balanced equation given below? Carbon disulfide plus 3 moles of oxygen, it gives 2 moles of SO2 plus 1 mole of CO2, that is carbon dioxide. So this is carbon disulfide and this is carbon dioxide. Right, now here 1 mole of carbon disulfide will produce 1 mole of carbon dioxide. Yes, 1 mole of carbon disulfide can produce 1 mole of carbon dioxide. It is totally correct. They are asking about false statement. Right, now here the reaction of 16 gram of oxygen can produce 7.3 gram of carbon dioxide. Come on, let us check with that. Here let me write the equation. Carbon disulfide plus 3 moles of oxygen, it can provide 2 moles of SO2 plus 1 mole of carbon dioxide. Here 16 gram of, here what they mentioned, 16 gram of oxygen, 16 gram of oxygen can produce 7.33 gram of carbon dioxide. Is it true? They are asking. Okay, now here molecular mass of oxygen, molar mass of oxygen, O2, here how much? 32 gram per mole. Right, so that means here 16 gram they mentioned. So 16 gram of oxygen, okay, 16 gram of oxygen, that is actually what it is, 0.5 mole. Right, now here what it is, 32 gram per mole, no? So that means here 16 gram means in that half only. So that means here 0.5 mole. I hope you got an idea. From this, here 3 moles of oxygen, 3 moles of oxygen can produce 1 mole of carbon dioxide. Okay, 3 moles of oxygen can provide 1 mole of, I just mentioned 3 moles of 3 moles of oxygen can produce 1 mole of carbon dioxide. Therefore, 0.5 moles of oxygen can produce how much of carbon dioxide? So here they have given what it is, 7.33 gram. Okay, now here mole we found in that half of that only, right? So here that means 0.5 mole of oxygen can produce how much of carbon dioxide? So here what it is, 0.5 divided by 3 equal to 1.66 moles of oxygen. So 1.66 moles of here moles of carbon dioxide. Okay, now here mass of carbon dioxide, how much? Here mass of carbon dioxide, it is 1.667 mole. This is mole into 44 gram per mole. That is mass of carbon dioxide. How do we identify? Mole into molecular mass. Okay, so we will get what it is, given mass. So this is given mass, right? Given mass of carbon dioxide. This is moles into molecular mass. I hope you got the clarity. Right now here when you calculate these two, you'll be getting what it is, 7.33 grams. So this is given mass. So 7.3. What in that question here? 16 gram of oxygen can produce 7.33 gram of carbon dioxide. This is also correct only. Now the next one, the reaction of 1 mole of oxygen will produce 2/3 moles of sulfur dioxide. See another statement here. Here also the same. So here the ratio of oxygen, how much? Now option C, the ratio of oxygen. So ratio of oxygen, that is actually SO2. So that is actually 3:2 they mentioned. No, see, I just mentioned the statements that it will be easy for you to understand. The reaction of 1 mole of oxygen will produce 2/3 mole of sulfur dioxide. Here 3 moles of oxygen can produce 2 moles of sulfur dioxide. But here 1 mole of oxygen will produce 2/3 mole of sulfur dioxide. So that means here in that ratio it is what it is. 3 moles of oxygen can produce 2 moles of sulfur dioxide. So here I just mentioned 3 moles of oxygen can produce 2 moles of sulfur dioxide. That is 3:2. So that in the question, what they have given, 1 mole of oxygen can produce what it is, 2/3 moles of sulfur dioxide. Here 1 mole of oxygen can produce. Here 1 mole of oxygen can produce what it is, 2/3 moles of sulfur dioxide. Exactly, 1 mole of oxygen can produce 2/3 moles of sulfur dioxide. 100% it is correct only. Right now 3 statement also correct. Now come on, let us check the last one. 6 molecules of oxygen requires 3 moles of sulfur dioxide. So here actually 3 moles of oxygen required 1 mole of sulfur dioxide to produce this compound. Now here 6 moles of oxygen requires 3 moles of 3 molecules of sulfur dioxide. Is it true? Come on, let us check here. And this point here, so here sulfur dioxide to oxygen, so that required how much? 1:3. So this is 3 moles of oxygen. 3 moles of oxygen required 1 mole of sulfur dioxide. Therefore 6 moles of what it is, oxygen. Here 6 moles of oxygen require how much? Here this one. Right now here, this I just mentioned here. So this is the question. Right now here, how much it is required? So 1:3 means here what they are asking, 6/3. So that means 6/3 means here 2 moles, right? 2 moles, right? So that means here what they are given. So here 6 moles of the question, 6 moles of oxygen require 3 moles of carbon dioxide. Now how is it possible here? Now here actually 6 moles of oxygen requires here 3 moles of carbon disulfide, means here 6/3 right now here in this only 6/3. So that means 2 moles only required, right? So 2 moles of carbon disulfide combined with 6 moles of oxygen, you will get what is the product. Right now which is the wrong option, means the last option it is wrong. I hope you got the clarity. Other 3 all correct. Which is the wrong option, which is the false statement here. So that means which is that exact answer you will get. You will get here 2 moles of carbon disulfide combined with the 6 moles of oxygen. Right? I hope you got the clarity. Come on, let us go to the next question. Which of the following setups here is correct to calculate the mass in grams of potassium chlorate produced from the reaction 0.150 moles of chlorine? Right now here in this point, calculate the mass in grams, that is given mass. So given mass equal to what it is. How do we identify that given mass? Moles into molar mass. That is what we can identify the given mass. Okay, now here moles into molar mass, they have given the moles. Right now here the equation they have provided, 3 moles of chlorine combined with the 6 moles of KOH, it can provide 5 moles of KCl 1 mole of KClO3 and 3 moles of H2O. Now the question they are asking about here 0.150 moles of chlorine into 1 mole of KClO3 divided by 3 moles of chlorine into 122.5 gram divided by 1 mole of KClO3. Right now, as we are seeing the options, the same thing, which is something differ, but here the calculate the mass in grams of potassium chlorate produced from the reaction of 0.15 moles of chlorine. So moles here, moles equal to given mass divided by molecular mass, right? So given mass only we have to identify. So given mass, how to identify? So given mass equal to moles into molar mass, molar mass. So moles into molar mass. So given mass here what it is? Moles 0.150 into molar mass of what it is here KClO3. So here molar mass of KClO3 it is 122.5 gram per mole. That is what you will get, that what it is given mass. I hope you got the clarity. This is very simple. Now how to identify? Here 3 moles of chlorine can produce 1 mole of potassium chlorate. Okay, now I just bring it here. 3 moles of chlorine can produce 1 mole of potassium chlorate. Okay, so therefore here 0.150 moles of chlorine can produce how much of what it is? Yeah, 0.150 moles of chlorine into 1 mole of KClO3 divided by 3 moles of chlorine. Exactly, it is correct. Into molecular mass of potassium chlorate divided by 1 mole of KClO3. Here, exactly, it is correct. Moles into molecular mass only. So here also they mentioned the same. Here 0.150 moles of chlorine into 1 mole of KClO3. Okay, this is 3 moles of chlorine can produce 1 mole of KClO3. Therefore, 0.150 moles of chlorine into 1 mole of KClO3 divided by 3 moles of, that is 1 by 3. Right, 1 by 3 of chlorine into molecular mass of potassium chlorate divided by 1 mole of KClO3. 100% it is correct what they have mentioned. The second point, the same idea, 0.150 moles of chlorine into 1 mole of KClO3 divided by 3 moles of Cl2 into 1 mole of KClO3 divided by, now this is ulta they mentioned, and the same way 0.150 moles of chlorine into 3 moles of chlorine divided by 1 mole of KClO3 into 122.5 gram per 1 mole of, no, this is actually all these three are wrong. Actually, how do we identify? This is given mass equal to, that is what, this is the format we can use. So moles equal to given mass by molecular mass. Right, now given mass, if they are asking moles into molecular mass, in that way we can identify. Hope you are getting. And the same point they are mentioning about 3 moles of chlorine can produce 1 mole of what it is, KClO3, therefore 0.150 moles of chlorine, how much? That's all, right? I hope you got the clarity. Come on, let's go to the next question. So which is the correct option? The first is the correct option. Come on. 2.0 gram of sample contains a mixture of SiO2 and Fe2O3. On very strong heating, it leaves a residue weighing 1.96 gram. The reaction responsible for loss of mass as given below. Here, Fe2O3 solid, it can provide Fe3O4 solid plus oxygen. It is actually unbalanced, they mentioned. Now, what is the percentage by mass of silicon dioxide and original sample? Right now here, 2 gram of sample contains silicon dioxide and iron oxide, that is Fe2O3 on very strong heating. Okay, now here loss of mass, how do we identify? Loss of mass equal to initial mass minus final mass. That means initial mass minus residue mass. Okay, initial mass minus residue. Right. Okay, now here this is actually what it is. They mentioned it is 2 gram. Okay, 2 gram. In that, how much it is? 1.96 gram. It leaves residue weighing 1.96 gram. Right now here, so 2 gram minus 1.96 gram. So that means here the mass of oxygen evolved. The mass of oxygen evolved. It is actually what it is, 0.04 gram, right? 0.04 gram. Now here unbalanced equation. This is unbalanced equation only. Now balancing that equation, actually Fe2O3, it gives Fe3O4 plus oxygen. This is what that, but here unbalanced equation, no? So how do we balance this? Actually, 6 moles of Fe2O3, ferrous oxide. Now this is ferric oxide. No, this is 4 moles of ferric oxide plus 1 mole of oxygen. So here 6 moles of ferrous oxide gives 1 mole of oxygen. 6 moles of ferrous oxide can produce 1 mole of oxygen. Therefore, here, what is the molecular mass of Fe2O3? Here, now I just mentioned 6 moles of what it is? Fe2O3 can produce 1 mole of oxygen, right? Therefore, 160 gram per mole. This is 160, no? 160 gram. Oh, this is 160, no? 160 gram per mole. This is molecular mass. 160 gram per mole can produce what it is? Molar mass of 32 gram per mole. So, oxygen, how much it is? 32 gram per mole. I just mentioned here moles. 6 moles of ferrous oxide can produce 1 mole of oxygen. The same way, 160 gram per mole of ferrous oxide can produce 32 gram per mole of oxygen. So, the mass of ferrous oxide. Okay, now let us check. Okay, now 1 mole of oxygen, that is 32 gram per mole, is produced from what it is? 6 moles of Fe2O3. Fe2O3. Right, so this is actually Fe2O3. What is the molecular mass of Fe2O3? It is 6 moles, no? So 160 gram per mole into 6. Can you get that point? So 160 into 6 moles. So you will get how much? 960 gram. Right, now here 1 mole of oxygen can produce 6 moles of ferrous oxide. The same way, 32 gram per mole of oxygen can produce what it is? 960 gram of ferrous oxide. I hope you got that point. Now, therefore, here 0.04. That is what now? 0.04 gram. Where do we get that 0.04 gram? It is initial mass minus residue. No, this point we got it right now. Here this is. So 0.04 gram of oxygen. Right. 0.04 gram of oxygen can produce from what it is. Right. The mass of Fe2O3 equal to 960 gram of Fe2O3 divided by 32 gram per mole of oxygen into what it is? 0.04 gram of oxygen, right? So now what is the answer you are getting? So you will be getting around 1.2 gram of Fe2O3. Now remaining mass in the original. So remaining mass in the original. Remaining mass and the original. It is actually original how much? 2 gram, right? 2 gram of the sample. Right, now here mass of silicon dioxide. Okay, so mass of silicon dioxide, what it is? 2 gram minus 1.2 gram, right? So 2 gram minus original mass minus remaining. So you will be getting what it is? 0.8 gram of mass of silicon dioxide. Now percentage of silicon dioxide, how do we identify percentage of silicon dioxide? So percentage of silicon dioxide, that is mass of silicon dioxide. Here just now we calculated, no? Mass of silicon dioxide, right? Silicon dioxide divided by what it is? Sample, original sample into 100 percentage, no, 100. So mass of silicon dioxide, it is 0.8 gram divided by this is 2 gram into 100. So how much you are getting? You are getting 40 percentage, right? How much percentage you are getting? 40 percentage. So here I hope percentage of silicon dioxide only they are asking. So percentage of silicon dioxide, it is 40 percentage. It is going around the neck, but it is very simple only the question. It is like a confusing way the questions have set, but still it is interesting. If you go through once again, so you'll get that clarity. Right now, which is the correct option? Option C is the correct option. Hope you got that clarity about this question. Come on, let's go to the next question. The next question, what volume of air at 1 atmospheric pressure and 273 Kelvin containing 21% of oxygen by volume is required to completely burn sulfur S8 present in 200 gram of sample, which contains 20% of inert material does not burn? Right now here, sulfur burns according to the reaction. So 1 by 8 S8 plus 1 mole of oxygen, it gives 1 mole of SO2. Now in the question they are asking volume. What is the exact volume of this reaction required? Right now here, given mass of S8, it is 200 gram of sample, which contains 20% of inert material does not burn. Okay, so given mass of S8, given mass of sulfur S8 equal to what it is, 200 gram into here 20 percentage they mentioned, no, which does not burn, that means it's remaining. So 20%, so which is consumed, it is actually 100 percentage, no, so 100 minus 20, so you will get 80 percentage. So 80 percentage we can mention it is 0.80, right? Can we mention in that way? 100 minus 20, it is 80. So you will get how much given mass? It is 160 gram, right? Now given mass, it is 160 gram. Okay, number of moles can be identified. So number of moles, how to identify? Given mass by molecular mass, it is actually what it is, number of moles. So number of moles equal to given mass by molecular mass. Right, so given mass, how much it is, just now we found, no, so that is 160 gram divided by molecular mass of S8. Actually molecular mass of S8, it is actually here 256 gram per mole. So atomic mass of sulfur into 8, so you will get 256 gram per mole. So number of moles of sulfur S8, you will get how much? 0.625 mole you will be getting. Right now here, what is the equation they mentioned? 1 by 8 mole of S8 plus 1 mole of oxygen gas. It is, right, this is solid and this is gas. It gives actually what it is? SO2. Right, now SO2, it's a gas or solid, of course 100% it is gaseous point. Now here 1 mole of oxygen required by every, this is 1 mole of oxygen required by every 1 by 8 moles of S8 sulfur, right? So S8 plus oxygen, it gives SO2. So therefore, here 1 mole of sulfur can required 8 moles of oxygen. It can provide 8 moles of sulfur dioxide. Can you get the point here? So 1 by 8 moles of sulfur combined with 1 mole of oxygen, it can provide 1 mole of sulfur. Therefore, 1 mole of sulfur combined with 8 moles of oxygen, it can provide what it is? 8 moles of sulfur. So here moles of oxygen required, right? Moles of oxygen required. Moles of oxygen required, it is actually 0.625 mole into 8 moles of oxygen. So here 8 moles of oxygen, how do we get it? Here S8, what is the mole? We got the answer here, 8, that is S8 moles of S8, it is 0.625 mole, and here 8 moles of oxygen required. So this is what we just moles of oxygen required to complete this reaction. So you will get, when you calculate this, you will get 5 moles of oxygen. So 5 moles of oxygen, we got that moles. Now we can identify the volume at STP. So volume of oxygen at STP equal to moles into volume in liter. So moles, how much? 5 moles into volume in liter, it is 22.4 liter. So you will get how much? You will get 112 liter. I hope you got the clarity. See, this is also like a same going around the neck, but it is actually simple, like how we have calculated the sixth question or something, like same like that only. Right now here given mass, how do we identify? So they have given a tricky way. So easily we can identify. Here 21% of oxygen by volume, it is required to completely burn of sulfur 8. So here given mass, it is 200 gram. Right now here in that 160 gram, it is a given mass we found, because it is 20% inert material which does not burn. So we got this one. Then next one, what it is here, number of moles of S8 we found, that is number of moles of sulfur 8, and number of moles of oxygen required through that balancing equation we found, and finally volume at STP, because they have given the temperature pressure constant. So we are getting 22.4 liter. So finally we are receiving that 112 liter, right? I hope you got the clarity. This is little bit higher level of these questions. Yeah, I hope you got some ideas all these questions. Thank you for watching, and thanks for your great support, and all the best for your upcoming exams.